Get started here. I appreciate all of you that have logged in to attend this presentation. The presentation today is entitled Choosing the Right Embedded Database Management Solution for Your Project. We'll be looking at build and buy considerations as part of this presentation. Just to kind of an introduction here, my name is Scott Meter. I am the Senior Manager for REMA. By the end of today's presentation, I'll hopefully give you some helpful things to consider when searching for the right data management solution for your next software development project. As an agenda today, we'll first be walking through a brief introduction into REMA, followed by what is data management, then discussing what are your requirements, followed by an in-depth overview of how do I make the right decision, which includes a look into architecture, database consideration, operation, and project. I will then conclude with a brief wrap-up. So what makes REMA authority on this subject? Well, let me give you a quick overview of our company's history. REMA is a privately owned company. We're based in Seattle, Washington. REMA, along with its database solutions, we're actually pioneers in the embedded database market. We're founded around 1982 by a couple of Boeing engineers. Our first product release was around 1984. In fact, our original founders are still with us today, including many engineers that have 15 or more years experience with our products. This really gives us years of cumulative experience in managing data within embedded systems. The REMA products have been estimated to be used by about 20,000 developers over the years, resulting in, of course, thousands of applications and probably 20 million or more successful deployments over the last 29 years since we've been in business. Just to kind of give you a view into our management background, it does come from many Fortune 100 companies, including Adobe, Boeing, CA, Microsoft, IBM, and Oracle or Sun that you see up there. Our core competence is database technologies and providing the most reliable solutions for collecting, storing, managing, and moving information. It's really our sole focus, which helps us serve the embedded marketplace much better as we're not fragmented between several different focuses like you might see with other companies in this business. Just wanted to quickly give you a glance into some of our example customers. You can find embedded databases used in virtually all vertical markets. Here we've listed those successfully using the REMA products within 5 verticals, that being business automation, telecom, industrial automation, aerospace and defense, and medical. So enough about REMA. Let's get down to this topic here. So what is data management software? It is loosely defined as any software that implements some type of data store. In other words, any application code that stores data. This can be in memory or on disk, so data stored may be volatile. At a minimum, to be considered data management software, it must be able to store and retrieve data. Beyond this basic definition, data management systems can vary quite a bit in the level of sophistication. Some examples of various features that introduce more sophistication are enforced data integrity rules, managing concurrency. This can be at various levels like multiple processes, threads, or tasks. Managing transactions. Here you may want to ensure that a complete transaction is saved, and if part of the transaction fails, the whole transaction is rolled back. And of course, managing relationships between data entities. Do you want to be able to associate information or data with other information or data stored in a different area? An example of this maybe is a sales or sales order information which is linked to sales order detail information. And of course, performing database recovery. If a catastrophic event occurs, can you recover the data, or is it gone for good? Performing hot online backup. Do you need to be able to back up your system while it is fully functional and online without the users having any type of system interrupt? And performing data replication or high availability. Is the system some type of mission critical system that has to be up 24/7, can't risk any failure or loss of data, such that you must maintain a replicated backup that can take over without any system interrupts should the main system have a problem or updates need to be performed. And finally, support for data synchronization. Do you have several systems and locations that need to remain in sync at all times? Other things to keep in mind is that a data management solution can be homegrown, in that in order to solve this project's data storage problems, developers in the company have chosen to write their own solution from scratch. Historically, writing your own solution has been the trend when demand for the other possible alternatives, like commercial or off-the-shelf solutions or open source solutions, has been lower. Within the last decade, the landscape has changed quite a bit. There's been hardware advances, demand for web connectivity, and increased application complexity. As a result, many projects are moving from maintaining and building their own solutions to more commercial offerings. So what are your requirements? So you have an application project and you're pondering the make or buy decision. In order to make a real educated decision, you need to list out your application data management requirements. These are typically very specific to an application and usually diverse and more often than not conflicting. Here are some questions to consider. Does your application require fast and predictable performance? Does your application require high availability and availability? In other words, must be up 24/7. Do you have minimal resources in which to manage complex information? Does your application need to interact with external systems? Does your application need to run against flash memory? Can you afford to lose data if the user pulls the plug or you have a system crash? When you run through your requirements, you will find that you have basically two options. Again, homegrown for the brave, meaning you're willing to take on the task of writing your own data management solution, QAing it, maintaining knowledgeable engineers who can document it, support it, update it as the application grows in complexity and requires more functionality. And then, of course, the commercial or open source solution, meaning you desire to pass on the burden of starting from scratch and purchase a solution from an established vendor that has longevity in this market, is well established, and can remove the cost and burden of building and maintaining your own. So using the 4 quadrants that I have in this diagram up on the screen will hopefully help you sort things out. In the 4 quadrants, we have architecture, database, operation, and project. Let's take a closer look at the first quadrant, architecture. There are 3 primary architectures to consider. The first is the standalone architecture, which has the following characteristics. The process here is links directly into the database manager, meaning the application code links directly into the database library. Each process has exclusive access to the database. This setup is very fast because there's really no conflicts with other processes. The second architecture is client-server, which is characterized by the fact that code can be partitioned on client and server, and concurrency and or locking is managed centrally by the server. Clients can be local or connected through the network, and network performance affects the clients. The third architecture is in memory, which is characterized by the fact that the database can be standalone or client-server. You also need to determine if your complete schema or database is going to be in memory, or can you have some tables in memory and some on a storage device. Also, can you configure in-memory data and in-memory indexes? Same type of question as the previous, which is, can I store data on disk or in RAM? Can I have a hybrid solution, or am I forced to choose all in memory or all persistent storage? And what about fault tolerance? How do I recover from a crash? Is the data in memory gone when someone pulls the plug, or does the solution have the ability to recover data? And finally to this is distributed. Here I need to determine if I need mirroring for remote read-only access. Do I need to be able to replicate from my embedded system into a third-party database, so going from my embedded solution that I choose into something like an Oracle system, a SQL server system, MySQL, DB2, those type of systems. And I need to figure out how to manage control of transaction traffic. So let's move over to the database quadrant, in which we'll cover data modeling, data types, storage, and partitioning. Data models are a way to attempt to represent the data structure of your real-world problem within a database solution. As you may know, this is seldom a trivial task. It can often be like trying to put a square peg into a round hole. This being said, however, there are three primary data models to work with. I'm going to talk about the first two, the first being relational, which I think many of us are familiar with, and the other being a network model. This includes the hierarchical model, which is really a subset of the network model. Some database solutions offer the best of both worlds in that they support the relational and the network model. As a side note, our RDM product, or our RAMA Database Manager, is one of those solutions. One point of clarification I'd like to make before moving on is many people think of SQL as being synonymous with a relational database. But although many relational databases have a SQL API, they're not one and the same. SQL is a procedural language used to manipulate data within a database regardless of the underlying data model. Also, the SQL engine is characterized by the fact that it returns data in the form of a table with columns and rows. Choosing the right data types for your data management solution is important and can affect your overall application performance. It will also impact your storage requirements and can determine how easy or difficult it will be to model your data. There are three primary categories of data types. There are simple data types. These are single-valued data types. They include C types like integers, long, float. If you are a C programmer out there, I'm sure you're aware with these. The other is SQL types like number, date, time. All C data types exist within the SQL types, in that integer and long are also SQL data types. There's complex data types that are multi-value data types. C types include arrays and structures, which most databases on the market don't handle. The SQL types defined post ANSI 99 are arrays and rows, which is equivalent to structures. To the best of our knowledge, these SQL data types have really only been implemented fully into enterprise database type solutions. And then there's bulk data types, which consist of two primary types, text and binary. Text handles large blocks of text or strings. Examples of these types are long, varchar, or clob. The other is binary, which include var binary, and blob, which stores undefined data like pictures and videos and really leaves it up to the application to define what the data is and how it should be handled. Now let's turn to storage. Chances are you will find that you need finite control on your database storage. You will also find that this level of control is very dependent on the database solution. Some offer more control than others, so consider the following. Table space control. Does the database management system allow me to map logical database tables to more than one physical file, or do I have to map all tables within one physical file? And can you set the page size used by the database? In the case where you are doing a lot of reads and not so many writes, record clustering can often increase performance. If you're doing a lot of inserts of new data, clustering isn't a good idea. So you need to weigh the time it takes to load a page into memory versus time benefit of having more records already in your cache memory. And then device control. How much control do you have over the devices? Is the data management solution dependent on the device types, or are they irrelevant to the data management solution? Many solutions are dependent on the operating system that a device is running on. If the device is running on an operating system not supported by the solution, the device can't be used. Some database management solutions, for instance, like our RDM database, don't care about the operating system as long as a communication protocol exists. Then there's relative location of physical files, which has an obvious effect on performance. Does your solution allow you to determine where the physical location is for your data? Can you have it both in memory or on disk? Can you store it locally or on a SAN? Can you control whether or not the database is read-only? Or does the database require read-write locks on the database in order to perform queries? This would cause performance or problems for devices like CD-ROMs or other read-only type devices. There's also the consideration of partitioning a database for LAN or WAN access and scalability. You have to think about localized transactions. Do you need the ability to handle unified queries? And what about being able to dynamically add partitions? Again, all things to think about, all things to consider. So data integrity is something that if the database doesn't enforce it, data integrity, your application will have to do it. So let's move into operation. This is one of the more difficult aspects of developing a database management system, and the level of data integrity controls can differ significantly across solutions. When looking at solutions, determine how important data integrity is to your application. Some applications don't store the data very long and don't care if the data gets dirty. Others do. So if data consistency is important, look for solutions that provide schema-defined referential integrity. If the data in the application can't be lost, look for solutions with data recovery capabilities. These will vary in their complexity as well. Some data recovery capabilities that you might consider are automatic database recovery. Let's say if Joe Smith cuts the power, can the database automatically restart and recover data to the point of the power loss, or do I need to call a database administrator? And then there's database mirroring and replication, which are components of high availability that provide data redundancy spread out over independent devices. Let's move on to concurrency, which is the capability for shared data. In the most basic scenario, it is the ability to view the same data at the same time. Most database solutions provide this capability, but once again, they are provided at different levels of complexity. The common lock levels are database locking, where all users are locked out of the database while a single user or process completes a transaction. Then there's table level locking. This was probably the most granular locking in the 1980s. And as it implies, the table will be locked to everyone except the person who has the lock on the table until they release the lock. Table locks are still commonly used if you are doing more bulk uploads to a table, because it is more efficient to lock the whole table rather than stepping through locking and releasing each page or row. Then we have page level locking, which is more granular than table, and the database tables are basically often spread over multiple pages. So if you can take a lock on a page, which represents a block of memory containing a subset of data, you leave the rest of the data or table or pages available to the other users. This lessens the probability that a user or process will be locked out. The more common level of locking that we see today is record or row level locking, which puts a lock on only the row or record that is being modified. This allows users to access any other row in the table that doesn't have a lock on it. This dramatically decreases the probability of a user not being able to access the data. Finally, there are field level locking options out there, and as it implies, it puts locks on the individual fields of a database record. This level of locking is currently only found in more enterprise database type solutions. When considering locking levels, remember that each level of granularity increases concurrency, but creates processing overhead. Transaction management is critical for guaranteeing data integrity and is also one of the more difficult capabilities to develop. If your application requires data integrity and your data management solution doesn't provide it, your application will need to do it. Things to look for in a database solution is whether or not it adheres to the ACID principles. So what does ACID refer to? Let's break that down. First are the transactions atomic. This refers to the ability of the database management system to guarantee that either or all of the changes in a transaction are performed or none of them are. Then we have consistency, which refers to the database being in a legal state when the transaction begins and when it ends. This means that a transaction can't break the rules or integrity constraints of the database. Then there's isolation, which refers to the protection each user process of the same database has from changes made by other user processes. A process will see a consistent database, and the processes will not see changes until a transaction is committed. One note on isolation, a good example of this may be in a bank transfer savings to checking type situation. Let's say you're transferring $1,000. You don't want your wife to see the savings account missing $1,000 and it not be present in the checking account. So there's one example of isolation. The other or final one is durability. This refers to the guarantee that once the user has been notified of a successful commit, the transaction will persist and not be undone. This means it will survive any system failure and that the database system has checked the integrity constraints and won't need to abort the transaction. So excluding hardware, what are the main performance factors to consider? Let's look at architecture and configuration. In-memory databases are going to provide the fastest performance because they don't require disk I/O. This is followed by the next best solution, which is standalone, because of the direct link to the database. Client server can be as fast as standalone if the code resides and runs on the server, which is then taking advantage of the power of the server and passing less information and processing onto the client. Data model and database features will also determine the performance and the ability of your application to scale. Typically, pointer-based joins are faster than index-based joins. Asynchronous transaction will provide better performance than synchronous transactions because they don't have to wait for one transaction to complete before starting the next. File I/O, if you are implementing a disk-based storage solution, will definitely factor into performance. Faster I/O, better performance. The interfaces to the database management solution will also play a big part in application performance. Navigational APIs are probably the fastest interface for transaction processing. SQL suffers from impedance mismatch, query optimization calculation, and execution. Excluding hardware, the main things that influence scalability are multi-threading. Does the database management solution utilize multi-threads, or is it at least thread safe? And does the database provide support for multi-core scalability? Very important here. And cache and file I/O efficiency also determines the scalability of your data management solution. And finally, what is the locking granularity? We've kind of looked at that. The final quadrant here in our diagram is project. Here we're going to cover footprint, interfaces, extensibility, and administration. In deeply embedded systems, footprint must be considered. Non-server type systems can probably deal with an executable footprint size of 500K to 1.5 megabytes. Lightly embedded systems where you find more client-server database architectures, you probably range from 1.6 megabyte to 2 megabytes of footprint range. Moving up the scale, you start moving really away from embedded systems and requiring embedded technologies more up into enterprise-type systems that might see executable footprint sizes of 80 megs plus. When you consider interfaces to use, you can look at industry standard interfaces or non-standard interfaces. Standard interfaces such as ADO.NET, ODBC, or JDBC, the next being SQL CAPI. Non-standard interfaces, again giving you probably the best performance, would be more low-level navigation APIs. Administrative APIs, which also give you more flexibility, customizability, and control to fine-tune the database to your exact performance needs and requirements. You also have languages to consider such as C, C++, or Java. When you look into client-server databases, you will notice that they typically support server-managed application code and stored procedures that really stored procedures look like virtual tables and can be a great way to move application logic over to the server for more efficient processing and faster performance. And then user-defined functions, which can allow you to wrap code into a single transaction across the network to also increase performance. Then there's non-server databases, which are typically customized at the source level. Really, the bottom line for embedded systems is you don't want to fill your application with the database administrator. It's just not possible to ship a live human being along with each software package that you deploy. And you really want your embedded system to run quietly in the background, unseen to the end user, doing its job quick and efficient. So in conclusion, with the increasing sophistication and complexity of embedded systems, the decision to buy a DBMS is gaining favor over building in a homegrown type solution. We, of course, have the build if you're brave, if you have a lot of time and money to spare, and if you probably haven't been listening to this presentation. And then, of course, we have the buy type solution if you want to avoid the unnecessary development risk that can go along with trying to roll your own and build your own solution. And if you want to leverage the expertise of a database vendor, and if you want really minimize reliability and support problems that come along with having to develop, maintain, QA, and add functionality to a data management solution that you have to build on your own. So we'll leave you with our mission statement here at REMA, which is really to provide the best knowledge or technology and competence to developers of embedded systems for collecting, storing, managing, and moving information while providing exceptional return on investment to our customers and shareholders. Certainly, if you have questions, let us know. We'd be happy to field those questions. We certainly appreciate you viewing this presentation. Hopefully we gave you some valuable points to consider when trying to choose the right embedded database management solution for your next project. Should you require more information, you can certainly go to www.rama.com. That's R-A-I-M-A. And we'd be happy to answer any questions that you might have. Again, we appreciate you attending this presentation. Thank you. Any questions online?